This is our first video over content. We're going to be talking about fluids. So the deal today is to get through talking about pressure as a basic idea, talking about density a little bit, something that you've covered a few times in lots of different places beforehand, and talking about buoyancy and the buoyant force. So let's jump into pressure. Pressure is defined as force per unit area. That's what pressure is, a force applied over an area. So if you want to calculate pressure, okay. In the next unit, we'll look more at the microscopic cause of pressure. It's actually a very cool thing and very fun way to think about stuff. But we'll do that in the thermo unit. Right now, we're just going to look at, in general, a fluid causing pressure. And so we're just going to look at that as a force over an area. Force is measured in newtons, area is measured in meters squared, and so our basic unit for pressure is the Newton per meter squared. That's a Pascal. That's what a PA is. But that is a tiny, tiny, tiny amount of pressure. 1 Pascal is small. So atmospheric pressure, what you and I are experiencing right now, at 15 pounds per square inch, is 101.3 kilopascals. Better yet, 101,300 pascals. Most of the time, we're going to write that as 10 to the 5th pascals. So 10 to the 5th pascals is 1 atmosphere. That's how we go back and forth between atmospheric pressure. We are going to just use pascals. We're not going to use atmospheres very much. So it's going to be good to know that 10 to the 5th pascals thing. We're going to use a lot. You're going to need it. So, what causes pressure? We're going to say that causes pressure is the weight of all of the fluid, so that's the gas and the liquid, above a surface. That's what causes pressure. The column of fluid, the column of gas above our surface. So let's look at just an example of how we would get pressure. We're going to look at a big water tank full of water, lots of water. And we're going to look at a 1 meter square on the bottom of that tank. The tank is 3 meters tall and it's full of water. And that's a 1 meter square. So what we're going to do is look at the pressure on that 1 meter square underneath of our tank. So what we want is the pressure at the bottom of the tank where that 1 meter square is. And it depends on the weight of all of the water right above it. So we need to figure out the mass of all that water above us. So we need to find a way to figure out the mass of that water column. Because I know weight, what I'm after, that's what's causing the pressure, is the mass times the acceleration due to gravity. So I need to find out what the mass of all that water is. And it's the mass of that water that we're concerned with in that red box. So we need the mass of that volume of water. So we're going to have to remember density. Okay. Density is the ratio of mass to volume for any given substance. The density of water, for example, okay, so that little symbol is a rho. We're not using a D anymore because we're adults now. Is mass divided by volume. For water, the density is 1,000 mass volume. That's density. The density for a given substance is always the same. If you cut it in half, you still have the same density. You have less mass, you have less volume. They move together. So in this case, our mass is going to be the density times the volume. Well, the density of water is 1,000 kilogram per meters cubed, And the volume is 1 meter by 1 meter by 3 meters. 3 meters is the height, 1 meter by 1 meter is the bottom. So the mass is going to be 1,000 times 1 times 1 times 3. Where the mass is going to be 3,000 kilograms of water. That makes the weight 30,000 newtons. And that makes the pressure 30,000 newtons divided by 1 meter squared, or 30,000 pascals. That is the pressure at the bottom of the tank of water. Now, there are a couple things that we need to add to this to kind of put it all together, because there are different ways that we talk about pressure. Pressure is force over area. We're just going to kind of look in general at what we just did. That force is weight over the area, or mass times the acceleration due to gravity over the area. So we need to find the mass to do that. So that's the weight of our fluid. That's our area. To get the weight, we needed the mass. So it was the density times the volume. So we're going to put that in there. So we're going to substitute the fact that mass is rho times volume. And now we're going to look at volume as area times height, or length times width times height. Area times height. So we're putting that in there. The areas go away. And so when we're talking about a fluid, the area is actually unimportant. All that really matters is the height of the column of fluid. The density of the fluid times the acceleration due to gravity times the height of the fluid. That's how we're going to find pressure from now on. So, for us, pressure is the force of a fluid on a surface, and pressure pushes in all directions. So if we go back and look at that tank we were just in, the pressure on the bottom pushes down, but the pressure on the sides of the tank push out, and it all pushes out the same, 30,000 newtons per meter squared. On your hand right now, air pressure is pushing up, down, and side to side. Because it's a fluid, it's going to push in all directions. Now, we talk about two different kinds of pressure. The first one is gauge pressure. This is the one that you're used to. Gauge pressure measures the pressure above atmospheric pressure. So if you use a tire gauge to get the pressure on your car tire, it's measuring the pressure above atmospheric pressure. So it's 33 pounds per square inch above atmospheric pressure. So for the problem we just did, okay, so for when using gauge pressure, atmospheric pressure is equal to 0. That's an important thing. So for what we just did, we'll get there. Absolute pressure, on the other hand, measures the pressure of the fluid plus atmospheric pressure. So absolute pressure is the fluid plus atmospheric pressure. So the way that we're going to do this is to say that absolute pressure is rho GH, the pressure of the fluid, plus the pressure of the atmosphere. That gives me absolute pressure. So for what we did on the last page, for that tank, the gauge pressure at the bottom is 30,000 pascals. That's just what we got from the fluid. That's our gauge pressure. But our absolute pressure is the gauge pressure, 30,000 pascals, plus 100,000 pascals of atmospheric pressure, giving me 130,000 pascals as absolute pressure. Gauge pressure, absolute pressure. Buoyancy is kind of the next thing we talk about after pressure. There are a couple ways of thinking about buoyancy. The one that makes the most sense to me is Archimedes' principle. What Archimedes said about buoyancy was that the buoyant force, or this effect of being buoyant, is the effect of a fluid being displaced by an object. So if you jump into the water, you push all of the water out of the way. Buoyancy is the water pushing back up on you to get you out. So the way we say that is the buoyant force is equal to the weight of the displaced fluid. Any object in a fluid experiences a buoyant force. This is important. Even an object that sinks experiences a buoyant force. So for a floating object, the buoyant force equals the weight of the object. That floating object has a net force acting on it as 0. The buoyant force is up, the weight is down, and they're equal to each other. For a sinking object, the buoyant force is, I wrote that backwards, for a sinking object, the buoyant force is, let me undo that real quick. For a sinking object, the buoyant force is less than the weight of the object. It's an important thing to keep in mind. Less than the weight of the weight wins, so the object sinks downward. So let's look at a quick example of buoyancy. We got a 1 meter cubed block with a mass of 1,200 kilograms, and we're putting it in water. You can tell it's water because it's blue. So we're going to look at the forces acting on this thing once it's in water. Weight is pulling down on it, and the buoyant force is pushing up. Weight is easy to find. The weight of the block is mg, 12,000 newtons. The buoyant force is the water pushing up on the block, and the buoyant force is equal to the weight of the displaced fluid. It's trying to get back to where it just was, in place of where it was, so it pushes up. So the buoyant force here is going to be the mass of the water displaced times the acceleration due to gravity. Now, in this case, the mass of the water displaced, okay, we'll get there. To get the mass of the water displaced, we need the density of water times the volume of the water displaced. Just like we did before. Mass is going to be density times volume. So for water, density of water times the volume of water. Now, in this case, because we're underwater, the volume of the displaced water is equal to the volume of the block displacing the water. So it's the density of water times the volume of the block times the acceleration due to gravity. So we get to put all that in there now to find the buoyant force. And we're substituting the volume of the block for the volume of the water because the block is under the water. Those two things are the same. So we have, for the density of water, 1,000 kilograms per meter cubed. The volume of my block happens to be 1 meter cubed, and the acceleration due to gravity is 10. So that gives me a buoyant force of 10,000 newtons. This object is sinking because the buoyant force is smaller than the weight of the block. Now, that's kind of what we need to know for buoyancy. We're going to do a lab and kind of do some practice to get used to this idea. But this is how we need to think of buoyancy, through Archimedes' principle. This next part is the technical cause of buoyancy, so if you're super interested, just pay attention. The technical cause of buoyancy is a pressure difference between the top of the object and the bottom of the object. So if we look at a block at the bottom of a column of water, it's a 1 meter cube box, underwater, under 5 meters of water. So we're in a little 5 meter water tank. You can tell it's water because it's blue. We're going to look at the pressure at the top of the box and the pressure at the bottom of the box. Pressure at the top of the box is rho GH. That's for the water because we're talking about the water. So 1,000 times 10 times height. And if it's the top of the box, my height is 4 meters. So it's 1,000 kilograms per meter cubed times 10 meters per second squared times 4 meters. That gives me 40,000 newtons per meter pressure on top of the box. Pressure on the bottom of the box, we're going to use 5 meters instead of 4. That comes out to be 50,000 pascals. So we have 50,000 pascals now. The difference between the top and the bottom is 10,000 pascals. And so if we look at that per square meter, for every square meter, we get 10,000 newtons. But that's the technical cause of buoyancy. If we understand Archimedes' principle, I feel like we're in a good place.